Saxon Advanced Mathematics, Lesson 72. Our topic today is a fun one, you guys. It's called the Law of Sines, and we're going to break through a really cool barrier that we've been living behind for a year and a half now. But before we dive into exactly what the Law of Sines is and what barrier it breaks, I want to back up and give you some information in case you're ever on Jeopardy! The word trigonometry is a Greek word, and it has two parts to it. The trigonon part means 3 angles, and the metry part means measure. Again, this is Greek. And so the two words put together means that trigonometry is the study of the measures of triangles, right? That's what we've been studying for quite some time. It started out with just the basic base times height divided by 2 area that we did, but our focus on trigonometry really started in earnest when we learned the trig functions, sine, cosine, and tangent. And using those, what we learned is that we could solve these right triangles that we've been working with, right? Remember that there are 6 parts to a triangle. There are 3 sides, and there are 3 lengths. Angles that we measure in degrees, and this gives us a total of 6 parts. And we have been solving triangles, which means finding all 6 parts, by using our really fun trig functions. So, for example, if we know that this angle is 50 degrees and this side is 4, we can solve the rest of that triangle. Because it's a right triangle, we can use our trig functions. And then we can say that, for example, for this one, we could say that the cosine of 50 degrees equals the adjacent 4 over the hypotenuse. And we can algebraically flip that around, right? We can say, if I cross multiply those and let them change places, h equals 4 over the cosine of 50 degrees. And we can find that on a calculator, right? And that will give us the hypotenuse. And then from there, we can use the Pythagorean Theorem to find the third side. And we can subtract 90 and 150 from 180 to get the third one, the third angle. So as long as we have one angle, no, that's not even true, because we can do it over here. We could do it with just 2 sides, right? Because we could say that the tangent of theta, or no, it wouldn't be the tangent, it would be adjacent over hypotenuse. It would be the cosine of theta equals adjacent 5 over hypotenuse 4, and that would allow us to solve for this angle. I don't know that one right off. So what we need to solve a right triangle we need one of the sides and then one side or angle. Okay? We had to have at least one side, but here we solved it with one other angle, and here we solved it with one other side. So to solve a right triangle, we can use sine, cosine, and tangent, and we need at least one side and then and one more piece of information, either another side or another angle, okay? And we've been doing this for quite some time and we've made marvelous headway. But now, at long last, we're going to ask the question, what can trig functions do to help us with triangles that are not right triangles? There's a special word. It's called oblique. L-I-Q-U-E, means all triangles that are not right triangles. All right, so they can be anything as long as they do not have a right angle in them. So here is a classic one. And there's a special way that we usually letter these. What we do is we name the angles, and we usually go from left to right as best we can. A, B, C. And those are the degree measurement of the three angles, okay? And then we have this, and we use uppercase letters for those. When we do the sides, we letter the sides, we name the sides so that they partner with their opposite angle. So if this is angle A, then this is side A, and we use a lowercase to measure that. B, angle B is here, so this would be side B, lowercase. And then angle C is over here. Now C is the tricky one because an uppercase C looks exactly like a lowercase c. So what I do when I'm doing these kinds of problems is I put a fancy whoop-de-doop in the top of the C so that I can tell that's the uppercase C, that's the angle. This is the lowercase c, that's the side. We create pairs of the matching letters, side over angle. And here is a fascinating thing. If we pair each side with its corresponding angle, and we create ratios out of those, they will all be equal. Whoa. The side over its matching angle equals another side over its matching angle equals the third side over its matching angle. So this is how we can use the trig functions, sine at least, we're just looking at sine right now. We can use trig functions even when we have an oblique triangle, a non-right triangle. It has no right angles in it. Now this one's slightly different, the requirements for this, because we have to have, we can solve this as long as we have, so what I'm doing is I'm making another chart. To solve an oblique triangle, oh, I forgot the U, sorry. Triangle. We need to have one side and then two, what we say, other parts. It can be angles or sides. Here we needed one side and one other part. Now we need one side and two other parts. Technically that's the same because before we had a matching angle there. So technically we had one side and one angle from the get-go, right? Because we knew that those matched. So the fact that it's a right triangle just gave us one more set of information. So oblique triangles have to work a little harder because they don't have that automatic matching right angle. Okay, so this is how we can use trig functions with oblique triangles, and we're going to set up these proportions with the law of sines. As long as we have at least one side and two other parts, it can be two angles, it can be two sides, or it can be one angle, one side. As long as we have a total of three and one of them's a side, we're good to go. So this is a fantastic puffy cloud of knowledge that is going to help us ever so much. All right, let's dive into an example. You'll definitely need your calculators at this point. So if you don't have one, grab one. If you paused me, welcome back. Here we go. I always write my angles in first. And again, here's the A, B, C. Those are the letters we almost always use for these kind of problems. And this is, oh, look how crookedy that got, sorry, 23 degrees. Now, as we're filling, and it says solve this triangle for the unknown parts. That's our instruction. As we're filling in, we look for pairs. We look for angles and their corresponding sides where we have both pieces of information given to us. And we see it's right here, right? So we're gonna set that up as our anchor proportion, right? Because this is technically a proportion. And we call it our anchor proportion because it has both numbers. No variables in this. So ours in this one is going to be side 7, an angle of 23 degrees. The side always goes on top. So 7 over the sine of 23 degrees will be equal to, which one should we put it equal to? Well, this isn't going to work very well because we can't put x and b. That would be two variables in the same equation. No bueno. So we're going to use side A and 10. So we'll say 10 over the sine of A degrees. This is going to be a little bit of a calculator workout, right? Okay, so now what we will do is we will cross multiply. We want to get this sine of A by itself because we can turn this into a number. That already is a number, that already is a number. Here's where our variable is. So what I'm going to do is cross multiply. I'll do that over here. 7 times the sine of A degrees equals 10 times the sine of 23 degrees. And then I'll divide both sides by 7. And then we'll get the sine of A degrees, because this will cancel, equals 10 times the sine of 23 degrees divided by 7. Okay, now before we dive in, let me remind you right here, we're trying to find the angle. Remember that when we, and this will be able to turn into a decimal number, right? Because we can find the sine of 23 degrees. Our calculator knows that. We can multiply it by 10 and divide by 7. This will become a decimal number. When we know the decimal and we want the degree, that is when we use the inverse button. So that's when we have to do second, and then we have to do sine to the minus 1. Right? It looks like reciprocal, but it's the inverse that we're actually doing, all right? So now you grab your calculator, you put in 23, you hit the regular sign button, that gives you a decimal number, you multiply it by 10, you divide it by 7, and what you will get is sine of A equals, you should get 0.5582. Okay, so that's just simplifying this part. Okay. Now, we take this, we use this situation, right? We enter 0.5582, then we hit second and the inverse sign button, and we get, I'm gonna have to flip. Let me leave it there and give you a second to work that. So you enter 0.5582, then you hit second and sine inverse. And what you will get is that A is equal to 33.93 degrees. All right? If you have any problem calculating this, let me know, and we'll work on that in the video chat. All right, so now we are looking for the first quadrant. It's positive, so we know there's a first quadrant angle that looks like this, right? 33.93 degrees there. But sine is positive in 2 quadrants. And this is going to get a little tricky, but just bear with me. This part we're used to doing. Okay, we know that sine is also positive in the 2nd quadrant. So there's an angle that looks like this, right? 33.93. If you're not sure which quadrant also has positive signs, you can check your unit circle. We don't have the actual measure of a 33.93 degree angle in the 2nd quadrant, but we know that sine is the 2nd number of the pair, and we can see, oh look, they're positive there. So here's another way you can use your unit circles, is just to double check your signs, your positive, negative signs of the sine function we're looking which is the other quadrant that has the positive values for sine. And if you don't remember, you can check there. Okay, so now we know it's 2nd quadrant. That means that this angle, which is one of the possible angles for our triangle, is going to be 180 minus 33.93, which comes to 146.07. So going back to our original problem, Paige, release yourself to me. There. We're trying to find angle A, right? That's what all of this drama has been about. So our choices are that A is either a 33.93 degree angle or it's a 146.07 degree angle. And this is one of the very few problems with the law of sines, is it creates what's called ambiguous results. Because we have 2 values for our angle. This won't happen when we use it to find a side. It creates 2 values for an angle, and we have to ask ourselves which is right, which is correct. And here's the way we can use common sense. Our choices are it's either a 33 degree angle or it's a 146 degree. Looking at this angle, do you think that could be a 146 degree angle? I don't think so. It's less than 90 degrees, isn't it? So we choose this as our correct answer, and we say that angle A equals 33.93 degrees, which is the way I would normally do that. Now we can go back here and say that A equals 33.93 degrees. Okay, so we use the law of sines to solve for this missing angle. Now we need to find out angle B. And that's pretty easy because we've got 2 of the angles. So we can say that angle B equals 180 minus the 23 degrees that we were given, minus the 33.93 that we found for, this is angle B, no, this is angle C, and this is angle A. I'm calling it angle C. We never called it that because we were given it. So it's 123.07. So we say that angle B equals 123.07 degrees. We did not have to use the law of sines to find that. We just subtracted because we had this one and we have this one now. So we just subtracted from 180. Okay, good. So this, I'm going to fill that in on my picture, and you can see there's a benefit to making your original diagram big enough so that you can fill in missing information, which is really helpful because we are trying to logic out each piece. Now all that's left for us to find is this. We can use our original anchor proportion and say x over the sine of 123 degrees, 0.07. If we set that equal to this, our original anchor proportion, then we should have it. So 7 over the sine of 23 degrees will equal x over the sine of 123.07 degrees, which is what B turned out to be. There it is there, and there it is there. Make sense? So now, that's degrees. So now, we're going to cross multiply, get that up here, right? You'll get really used to being able to do the cross multiplying in your head. Technically, we multiply this by this, that by that, then this will be up here, and we divide it away. If you need to do it in slow motion, do it in slow motion, but at this point, I think you guys are perfectly capable of jumping into this. So 7 times the sine of 123.07 degrees divided by the sine of 23 degrees equals x. This you can run through your calculator, 123.07. The regular sine function, because in this one we know the degrees and we want the decimal number. So 123, regular sine button, times 7, divided by parentheses 23 sine. I don't know if you need to hit equals or not. You might need to hit equals. Close parentheses equals, and that should give you a value of 15.01. And that is the measure of x. Oh, this page right here should be 15.01 units long, and that looks logical because if that's 7 and that's 10, this one should be a little bit bigger, right? That looks about right. And my triangle is roughly approximate to what is in the book, the picture. Okay, so what we have done is we've used the law of sines in a couple different ways to solve for the missing pieces. We also used our simple rule that the 3 angles of a triangle add up to 180. And we also used some common sense in interpreting this ambiguous results. Because when we use the law of sines to solve for an angle, we get 2 values. And so we have to use logic to figure out which is correct. All right, we did not have that problem here when we used the law of sines to find the side. That does not yield ambiguous results. It's only for the angle. Let's do another one. There are 3 problems in all in this lesson. The last one is shorter. The next one is long. Example 72.2. I'm going to draw my triangle a little bit bigger this time. Obtuse triangles that go that way always need a little bit more space. All right, this is angle A. We don't know what it is. This is angle B. And this is angle 23. Oh, this is like the problem we did last time, right? Interesting. This is 10, this is 7, and this is x. Look, you guys, it's the very same numbers that we had last time, right? 7, 10, square root of 23. 7, 10, square root of 23, a, b, and x. Ah, okay, interesting. All right, so let's go through and work it just like we did the last one. Here's our anchor proportion. This is where we have an angle and a side that are partners. And so they'll be our anchor. I'm gonna write them up. I'm gonna write them here. 7 over the sine of 23 degrees. And then let's do the same thing we did last time. It worked out pretty well. 10 over the sine of a degrees. All right, this seems really familiar, doesn't it? Let's look back and see what happened last time. there it is. We used some algebra, we slid it around. We summarized all this part on the calculator. Then we used our inverse trig sign to come up with a value. And, oh yeah, remember, we found that A equals 33.93, and then we realized there was a first or a second quadrant angle that would work for that particular value. And we said, oh yeah, that's the ambiguous results, because trig functions give us 2 quadrants for each answer we create, right? This was a positive angle measurement. And so we had 2 different options. Okay, we decided that we needed to use this one because we looked at our picture and we said, oh, it's less than 90 degrees. But now, look what's happening. Don't you think that this looks like it could be the 146 degree angle? Right? That's what John did. He gave us a different shaped triangle so that we can practice using the other value. So, remember, we put the 33 here, but in order to find this measure, we have to take 180 and subtract the 33. So this is the size of our angle, 146.07. In this problem, because the drawing of our triangle tells us that it must be different. So this equals 146.07. Now when we calculate B, I'm going to write angle A, angle B equals 180 minus 146.07 minus the 23 that we already had. So angle B is now equal to a measly 10.93 degrees. Okay, so that's a really nice illustration of how that ambiguous result can be interpreted differently based on the picture. And we do, you guys, we just have to rely on the picture. So that's a little weird. Okay, we got this one. We got this one. I'm just gonna write angle B again because I like to put my variable close to my answer so I can see. Now all we have to do is solve for x. And we can do that by saying 7 over the sine of 23 degrees. That's our original anchor proportion. Now we're going to use it for this. Equals x over the sine of 10.93 degrees. Right? We algebraically flip it around. We cross multiply. This will end up on the bottom. So we say 7 times the sine of 10.93 degrees divided by the sine of 23. Use your parentheses down here on your calculator. And that will get us to 3.40. That is the length of side x. And my drawing, it looks a little wonky, but if you look in the book, that's a totally believable length. And even so, it makes sense. This is definitely the shortest of the 3 sides. So 3 seems like a reasonable conclusion. All right, so this problem was about interpreting the ambiguous result differently. And we saw that this is clearly bigger than a right triangle. So we chose the larger value of our calculation. Okay, one more problem. Are you ready? Example 72.3. Isn't this kind of fun? It's so fun to finally be using trig functions and not be tied to right triangles. We can take them out into the world and show them around to other triangles, and it's just happy, happy days. All right. Here's our last triangle for this lesson. This time John's putting the A up here, which I normally wouldn't do. I'd always put the A down here, but he's mixing it up. John's feeling his oats. Okay, so we have 2 of the angles, and then we need to have at least one side. Yep, there it is, 7, M, and K. Again, I don't like this. I don't like that he's mixing up our usual standard pattern of uppercase, lowercase, they match as you go across. That bothers me. But we can see we still have an anchor pair, don't we? This and this are going to work out fine. Now, as I'm circling things and looking at it, I realize A is going to be really easy because we already have 2 of the angles, right? We've already got a 50 and a 30. That's 80. They have to total 180, so A has to be 100-degree angle. Oh, that's so easy, right? So don't forget you can use the easy stuff too. But we can't use Pythagorean in these because Pythagorean only works when it's a right triangle. So, no Pythagorean for oblique triangles. Okay? Sad days. There. A little tear dripping out. Okay? So we can't do that, but we can use the law of sines. It's fine. So here's our anchor proportion. We're going to say 7 over the sine of 30 degrees will equal K over the sine of 100 degrees. And then we can do the same things, just set up the second part of the problem. Sine of 7 over the sine of 30 degrees equals M over the sine of 50 degrees. What I especially like about these 2 equations that we're going to solve, these 2 proportions, is that in both cases we have the angle and we're solving for the side. I don't have to worry about ambiguous results for these sides. For sides, right? Ambiguous results just are when we're solving for the angle. So that takes a lot of the work out of it. I will show you how we algebraically flip this, right? K will be equal to 7 times the sine of 100 divided by the sine of 30. And M will be equal to 7 times the sine of 50 degrees divided by the sine of 30 degrees. Run those through your calculator. Do it right now. I will pause and give you a chance to work, and then I'll write in the answers, and that will be the end of our lesson. Yay! So M equals 10.72, K equals 13.79. Those are the lengths of these 2 sides. I'll just write them in up here because I think it looks nice to see the triangle all filled in, all 6 parts. We again check for reasonableness. If this is 7, that's 10, that's 13. That looks reasonable. If this was 2 and this was 1, I would worry. If this was 65 and this was 112, I would be gravely concerned. But that's not what we got. So here are 2 of our answers. And remember, we started this one with 1 side and 2 angles. So it fits to our rule. As long as we have 1 side and 2 other pieces, we can solve for anything. Remember, Jayla, I told you this. I can't speak for Laura and Vivian. But way back on the first day when we did trig functions for the very first time in the red book, somewhere around lesson 40, I told you they only worked in right triangles. But I gave you a little footnote and said eventually, someday, I will show you how they work for other kinds of triangles. But for now, right triangles are the only things trig functions are good for. Today is the day. Today is the day that you finally learn how to use the trig functions with non-right triangles. It's a little bit messier, but it works. So, hallelujah. Thank God for trig functions. Goodbye.